Okay, so this first tutorial will deal with organic semiconductors, and we will look at a very specific class of organic semiconductors. And I have foreseen two parts. In the first part, that relates mainly on a few essential concepts that we need to characterize organic semiconductors. And as you will see, that this relates very strongly to the band gap and the band gap engineering, how you can do that, how that relates the band gap with structural parameters. And in the second lecture, we will go into more concerning the synthetic methods that are used. These are organic semiconductors. Okay, organic chemistry is used then to make these materials. This is a little bit an outline of the first part, so I will start with a small introduction. Then we will go into how the band gap is determined, and there are different ways to do that. We will look at the most simple ones. I will not treat the more complicated ones. But this allows us to look at how you can engineer the band gap, how that relates to the molecular structure. And there's a final item that I want to discuss, that band gap is not only determined by intramolecular aspects of intrastructural aspects, but also intermolecular effects, so that there are interactions between molecules, separate molecules. So if we talk here about organic semiconductors, even there I have to be specific. We are dealing with so-called conjugated polymers. Now, in a conjugated polymer, you can easily recognize that, because in all these structures that I show here, you see that you have a system in which you have a single bond alternating with a double bond, and this repeats itself in all the structures that you can see. So these are all conjugate polymers, some with a backbone only consisting of carbon. Here you have an example where there's a sulfur atom, but this could also be nitrogen or oxygen or whatever. What you also see is that all these structures have these tails. Now these tails are intended for processability. So at some point you want to dissolve the material, you want to process the material into a device. And therefore you need this kind of side chains. Without side chains, these materials are not processable. These kind of semiconductors are the basis for plastic electronics, also called organic electronics. That depends a little bit on what kind of definition you want to use. Now, where's that coming from? Actually, a very important person in this respect was Richard Friend from Cavendish Laboratories. He was actually the first one who really studied the semiconductor properties of conjugate polymers. But there's also another guy, Alan Heeger. He discovered about 40 years ago organic conductors and the use of conjugated polymers, not for semiconducting but for conducting. And it's actually the competition between these two gentlemen over the year that has pushed the field forward. A lot of progress has been made, and okay, some people look at this kind of electronics as a key technology for the 21st century. It's surely so that a lot of type of devices has been developed by now. So you can effectively use these organic semiconductors in LEDs, transistors, sensors, solar cells, whatever you want to imagine, detectors and so on. So in principle there's a wide area of application. Now what Richard discovered is actually based on this material. That's a so-called PPV, so phenylene vinylene. The vinylene points to the double bond. You see here the decoration for solubility. So in 1990 it was published in a paper of Nature that this material showed electroluminescence. These materials are very nicely colored, most of these materials absorb invisible light, so they have a true color of their own, and quite often they are also fluorescent. Now what Richard discovered was that building this layer, this polymer into a device, that electronically you could create fluorescence. And this is actually the principle of a polymer LED. Now the light that is emitted by the LED is of course in one way or the other related to the structure of the polymer. So we want to go into that. So to explain that, quite often one uses a so-called band model that comes from solid state physics, and in your education you have certainly heard or encountered these concepts of the valence band. Here they are a continuum of energy levels that are filled with electrons. You have also a continuum of levels that are not filled, that are empty, and in between there's a forbidden energy zone that's called the band gap. And in this simple description one can say, okay, the band gap determines the electronic and optical properties. If it is quite large, you have an insulator. It also will be transparent, for example, or will not absorb light. If you have no band gap, you would expect that it behaves as a metal. And if the band gap is somewhere in such a way that it absorbs invisible light, so that you have a band gap, let's say, well, actually from 1 eV till, let's say, in practical sense, 3 eV for organic semiconductors, then you will have a semiconductor, which means that just by thermal excitation you can excite an electron from the valence band to the conduction band, create charge carriers, and in this way you create a certain conductivity. Now specifically for conjugate polymers one has mostly this case, and as I mentioned, from 1 eV more or less till something like 3.5 max. Yeah? So that's the model we want to use. Is this model correct? No. It's a very approximative approach. So if you go in detail in modeling, you will see that this model doesn't work. But for conceptual reasons, if you want to understand what we are dealing with, this is good enough. And in the context of this tutorial, I will only use that. Okay. If you then look at the conjugate material, so the excited state looks like this. That's called a polaron exciton. And this will emit light by relaxation of this electron to the ground state, to the lower level energy state. Now, if this material emits light, okay, this light can be of different colors. Okay, you end up with the ground state as mentioned here, but you can end up with different colors, red light, green light, or blue light. What kind of light is emitted depends on how large this energy gap is. In first instance, the band gap, this initial gap. This initial gap will determine how large this gap will be, which determines then the type of light that's coming out. So that means that if you want to have blue light, you need a higher band gap than when you want to have green light or red light. So the band gap determines for an LED the color of the device you are creating. Now for solar cells it's identical. Actually this is a reverse process. You start with a ground state and you want to create an excited state, a polaron exciton, which then can be broken up in individual charge carriers, bring it to the electrodes, and in this way you have again a device, in this case a solar cell. Also here, the type of light that can be absorbed depends on the band gap of the material, the band gap of the polymer. So if you want to absorb red light, green light, or blue light, again you have to tune the band gap in such a way that it fits to the energy of this light. So the band gap is a very critical concept in understanding and describing the behavior of these materials. So that's mostly also the first thing that one determines if one has a new organic semiconductor or a new conjugate polymer. What's the band gap? So how can you determine that? Well, actually there are two approaches. The most simple one is just looking at the absorption spectrum. Here you have a conjugate polymer that's used for solar cells. There are three derivatives on these positions. Fluoroatoms are built in, or here, or there, or these are replaced by hydrogens, so that's the three types. Now you see that they have different absorption spectrum. And actually, from the onset of the absorption band, you can make an estimate of the band gap. So it's quite easy. You draw the tangent to the higher wavelength side of the absorption band, and in these three cases, you see that they shift to a shorter band, shorter wavelength, which means that introducing these fluoroatoms widens up the band gap actually. And if you have then the baseline, okay, you have the intersections, you find these onsets in nanometers, and with this formula you can then calculate the band gap. That's the easiest way. Another approach is based on electrochemistry. So you can do cyclic voltammetry, so you scan your film in a cell over different potentials. Here are typical examples. And once you are able to oxidize the material or to reduce the material, you will measure a current. And in this way you can nicely follow oxidation processes, and after oxidation maybe reduction or reduction and then back oxidation to the neutral state. Now these, the onsets of these oxidation potentials can be translated. Let's say this is not rocket science. You have to look at it as a kind of empirical formula, but this can be related to the HOMO level and the LUMO level. So the advantage of electrochemistry is for sure that it doesn't only give you an idea by measuring this distance of the band gap, but also where you would estimate the HOMO energy level and the LUMO energy level. And that's, let's say, as far as you can see both processes. Sometimes you only see oxidation. Then it's more difficult to determine the LUMO level. But even there are some tricks. So this is quite often referred to as the electrochemical band gap. Now, in principle, there is only one band gap, and that's the optical one. That's the most closest to the definition. As we will see, it's not totally correct even. But in the electrochemical band gap, what can happen is that when you extract electrons out of your film, this has to be compensated by counter ions that go into the film. Now this moving of counter ions can be hampered because the density of the film. And that means then that you need extra potential to push in the counter ions. And so quite often you see that this so-called electrochemical band gap is larger than the optical band gap. And that's because this overpotential that you need to push in the counter ions. In some cases this fits very nicely that the optical band gap is exactly the same as the electrochemical band gap. But it can differ. Now a final remark that I have to make, and that's a remark that was made by Jean-Luc Brida very recently actually, that he, let's say, emphasized that these kind of definitions are not the real band gap. Because if you look at the real definition, the band gap is determined by the difference between the ionization potential and the electron affinity. And the question is, if you do an excitation from the ground state to the first excited state, the singlet state, is this the same process as this difference between ionization potential and electron affinity? And that's not true. You can imagine it very simply. What do you do with the ionization potential? You take an electron out of the HOMO and you bring it to infinity. So there's no binding anymore between this electron and the nucleus of the atom. Electron affinity is the reverse. You bring an electron from infinity and you bring it close to the nucleus. And so you expect a binding, and that's the reason why this is lower than that. So there's a binding because it feels the nucleus. Now, what you do here is you bring an electron from the HOMO a little bit higher. So even this electron feels the nucleus. So it is not, has not been removed to infinity or something like that. So what the difference is between these two and that, you can expect that is actually this binding energy of this electron, the LUMO, with the nucleus. And that's what was emphasized by Jean-Luc Brida in this very nice paper. This is the fundamental band gap, and it differs from the optical one with this binding energy. Now, how large is that? So what's the error that you make? Depending on the source, somewhere between 0.1, 0.2, 0.3 eV. The largest values you can find, well, because there's always an estimate, something like 0.3. This is an important point to make. Actually, you do a kind of approximation. But quite often this works because you compare different materials. So it's always in a relative context that you use this concept of band gap. So that's independent of this criticism, it works. Now, another concept that we have to define is the effective conjugation length. So when you look at a series of oligomers, you have here an example. This is from a paper some 10 years ago, where they have synthesized a series of compounds where this part is extended. So, and as these are conjugate systems, they feel each other. So your system becomes larger and larger, and typically what you see in the optical spectra is that this onset of the absorption band, that shifts to longer and longer wavelength. That is because if the system is more delocalized, the energy levels of HOMO and LUMO come closer together. Now what you also see is, and that's very typical, that the change, the difference between this onset and this onset, between monomer and dimer, is much larger than the following ones. So it seems that this effect of the length of the oligomer on the absorption spectrum, that this levels off, that there's a kind of saturation effect. And it's effectively like that. If you go to an oligomer with 9 or 10, let's say 11 repeating units, you will see that this onset doesn't change anymore. Where is this coming from? Well, quite often, and a lot of papers that you find in literature, they typically refer to the fact, yes, this is a flexible system and this is not flat, so you have torsion angles, so it is, there's a kind of angle between the different planes, and so the interaction is not that effective, and by consequence, your band gap doesn't increase to that extent that you would expect. Okay, it's quite often said, this effect exists, but this is not fundamental. Before I show you the other example, I have to define the conjugation length and the difference with the effective conjugation length. So the conjugation length is how large your pi system is if you draw the structure. You can count the number of double bonds that are alternating with single bonds. And how far you can reach that determines how large your conjugate system is. The effective conjugation length is the extent to which this conjugation length affects the absorption spectrum. So as I mentioned before, typically you see that there is a saturation at 10 repeating units, for example. Even if the conjugate system is 20 or 30 repeating units, still the absorption spectrum will look the same as for an oligomer of 10. So the effective conjugation length is then 10 repeating units, or the equivalent of 10 double bonds that are in the structure. So that's actually the difference. Now, as I mentioned, this difference is quite often referred to differences in conformation, that you have torsion angles, that the system is not totally flat. The different repeating units don't interact perfectly. Okay, here you see a kind of counter-example. Here you have a series of oligomers, that's a more recent paper, of, let's say, a kind of polytyrphene, where all the tyrphene rings are fused. And so you have a tetramer, a pentamer, a hexamer. They even made the heptamer till the octamer. And here you see then the different absorption spectra. So this system, this pi system, is totally flat. So there cannot be any torsion effect. Still, if you look at the onset of the absorption bands, of the absorption spectrum, you see that this onset shows the same behavior. So the first is the change larger, and as your oligomers become longer and longer, you will get a saturation. This is also typically visible when you plot the onset of the absorption band against the inverse of the chain length. Typically, you get a straight line. And the straight line means, because it's the inverse of the chain length, that this is a function that saturates. So even for this system, you get this straight relationship. And here it's also theoretically modeled. This is a theoretical modeling, and okay, it's a little bit different, but still it's quite similar. So also here you see this effect. Now, where is this effect fundamentally then coming from? Actually, this is coming from the fact that if you have a one-dimensional system, as conjugated polymers are mostly, an excitation, every excitation is localized. Even if your system is very long, it will be localized. That has to do with the fact that every excitation relates to this kind of structure. It's called a soliton-antisoliton pair. This is not stable, but this gives this energy levels in the gap. You will see this energy levels as soon as you excite, because then you have an electron on both energy levels, and this can exist. The soliton-antisoliton pair will never exist. The reason is quite simple, because the energetics of this structure is totally different from that structure. This is a benzene ring, and you have aromaticity over here. This is a Kinowitz system, and the aromaticity, or let's say the so-called delocalization energy, is very low. That's a difference of 30 kilojoule. Sorry, not kilojoule, kilocalorie per mole. So it's over 130 kilojoule per mole per repeating unit. So when you make this intermediate part larger and larger and larger, you will lose energy. So the system has a tendency to confine such an excitation and localize it. So your excited state is localized, and that's the reason why, if you look at absorption spectrum, there is a limit to what extent the onset can shift. Okay, I mentioned that this should be a straight line. Now even that is an approximation, and there's some work of Johan Girchner. He made a paper in 2013 where, let's say, experimental data and computed data were overlaid, and you see, yeah, and that's also the trouble a little bit, that mostly one has only a limited series of oligomers. Okay, in a limited series of points you can always make a straight line, but effectively you see that this is actually a curve, and here this is demonstrated for different type of conjugated polymers. So one has to be aware also that in this field a lot of approximations are used. That's not a problem, as long as one is knowing what one is doing. Good. Let's move now to bandgap engineering. Actually, the basis is relatively simple. There is a relationship between the bandgap and the molecular structure. And it can be nicely demonstrated for polythiophene. This is how polythiophene normally looks like, and we think of a structure that's infinitive. So there are no end groups. Now, in that case, there are on the energy surface of the ground state, there are two minima for two geometries. One is called aromatic geometry, and people familiar with aromaticity or organic chemistry recognize here an aromatic structure. The other minimum in the energy surface is this geometry, where you have double bonds instead of single bonds between repeating units. And so that's called the kinetic geometry. They differ in stability. The difference is actually the aromaticity. This is aromatic, this is non-aromatic. And okay, that translates to stabilization for this structure. But if you look then on the band gap, also there you see a substantial difference. Here for polythiophene you have an estimated band gap of 1.8. For the kinetic geometry it's much smaller. That's only 0.5. Okay, let's say this was modeled. So here you see a clear relationship between structure and band gap. But this was modeled by Jean-Luc Brida many, many years ago, in which he systematically changed the geometry from aromatic till kinetic, and look then at the evolution of the band gap. Now you see here a straight line. I have to point out that what is here used as a parameter, so it's a parameter of geometry. Actually, this is a very simple one. So one takes in this case, the bond length of the double bond of the ring, and then the bond length of the adjacent connection with the following repeating unit, which is a single bond, and which will be longer. And this difference one calls then the bond length alternation. If this is a short bond and this is a longer bond, okay, if I make this difference, it will be a negative value. If I take the kinetic geometry, then this one is long and this one is short, I will get a positive value. So with a very simple parameter, you can easily plot in such a figure. You can follow the change in geometry from one to the other. Here you have a strongly aromatic structure, here you have a strongly kinetic structure. What's clear that as the difference between these two bond lengths goes down, also the band gap goes down. Now what does that mean? Now we can look at that with a concept that comes from organic chemistry, in which one uses so-called resonance structures. Resonance structures are localized representations of reality. So reality is this, and okay, we can describe that by making linear combination of totally localized structure for the polythiophene like we know it, and the one of the Kindred structure. If we move on along this line, this will just mean that when in our starting point, this contribution to the real structure will be large, and this will be small. As I move here, the bond length difference goes down, so that means that seemingly, this bond, double bond, becomes longer, and this becomes shorter, and this way the bond length declination goes down, which can be described by a higher contribution of this. And actually, at this point, I expect that the contributions are equal. Now, if you have a structure, a delocalized structure, in which two resonance forms have an equal contribution, then we are talking about perfect delocalization. So actually this term, which goes along with different contributions of these resonance forms, is a measure of the quality of intrachain delocalization. And that's the role of bond length alternation. Actually, if you would determine the bond length alternation, you actually determine the quality of the intrachain delocalization. The more perfect, the lower the bond length alternation. Okay, now here I want to refer to a review paper that was published by Jean Roncalli many years ago, in which he wanted to describe the different structural effects and how they affected the band gap. And he explained that as a summation of 5 terms. So it looks a little bit like a mathematical formula. And these are the different terms: bond length alternation, deviation from planarity, aromatic resonance energy, inductive and mesomeric effects, and then intermolecular effects. Although this review paper is still very interesting because of the examples that he has collected and with which he illustrates certain effects, this presentation, this description actually, is fundamentally wrong. And it's used quite often in literature. Why it is wrong? Well, actually very simply, because this is not a mathematical formula. If you would write down something like that in mathematics, you would assume that all these parameters are not dependent of each other. They should be orthogonal. It's like vectors. But that's not true. That's not true. If you analyze what's going on here, a lot of these effects are intermixing. And so this is not a well representation. So I will present an alternative, which is more correct and also allows you to place all these effects on the right spot. We will see, for example, that this bond length alternation is not an effect, it's a measure. It's your stick with which you measure delocalization, nothing else. Okay, in this approach, we start with an imaginary situation in which you have the repeating units on an infinite distance from each other, so they don't interact. And then you will have, if you look at the energy levels, you will have the HOMO level and the LUMO level, and they will be separated by a certain energy distance, so the HOMO-LUMO gap. And now we want to look at, okay, what happens if you bring them closer and closer to each other. And they start to interact. And in the final state, you end up with the situation of the polymer. What you then will see is that this description transfers to this description. That you have a conduction band, a valence band, and in between you have the energy gap, the band gap. Now, what happens? Well, when you compare the initial situation with repeating units not interacting with each other, if you bring them closer together, the energy levels or the orbitals, the molecular orbitals, will mix because of the interaction. And you get bonding combinations and anti-bonding combinations. And so you get a collection of energy levels as a consequence of the fact that you combine an infinite number, if you look at an infinite long polymer, an infinite number of building blocks. And so it disperses. So as it disperses, the band gap goes down. So the stronger the interaction between the repeating units, you can expect that the band gap goes down. So actually, the band gap is related with the quality of the intrachain delocalization along the contour length of the polymer. That's what's going on. You can easily look into that in more detail if you would look. So this is the total continuum because you have an infinite number of repeating units. You have an infinite number of energy levels. All these energy levels are in one way a combination of the LUMO, in this case, because it is for the valence band, of thiophene. And here you look at the bottom, the lowest energy. This is the totally bonding combination. If you look at the top, you see the anti-bonding, totally anti-bonding combination. And in between you have all the possible permutations with a low number of anti-bonding interactions, a lot of bonding interactions, or a large number of anti-bonding and not so many bonding interactions. And the same is true for the HOMO. So if you look at the bottom and the top, you will see respectively the bonding combinations or the anti-bonding combinations. And so the higher the quality of the delocalization, the lower the band gap alternation will be, and the smaller the band gap will be. Because a strong interaction, strong delocalization, will make the dispersion of the bands large. And so what's left over reduces. That's as simple as that. So that's a better way of looking at it. Actually, what we are dealing with, and one can understand the different effects in a better way from there, that there's a competition. A competition because mostly you have a ring system as your repeating unit. This internally is delocalized, and there is a competition between delocalizing in the repeating unit, dus localizing it in the repeating unit, or delocalizing along the contour length of the polymer. The more it is localized in the repeating unit, the higher the band gap will be. The more it can choose for delocalization along the contour length, the larger the dispersion will be and the lower the band gap will be. So this is fundamentally what's going on. And that's a better description, as I mentioned, than the one of Roncalli. And we measure that, we measure this competition by the bond length alternation. So if I could measure that, I could really put a figure on this competition. So the question is, how can I engineer that? How I can engineer the band gap knowing that? And the answer is very simple, aromaticity. Aromaticity will localize the delocalization in the repeating unit. The more aromatic, the stronger. By lowering aromaticity, delocalization along the polymer chain will win, and so your band gap goes down. A few examples. So this is polythiophene, is an aromatic structure. Let's say there's historically has been an effort to move this to this structure, polyisotinephthane. Expectation was that the band gap was only half an electron volt. Actually, this material was synthesized and it had a band gap of 1.1. At that moment, nobody cared. that there was a deviation. It was assumed that this putting this 6-membered ring or these 2 extra double bonds on top of the thiophene ring would reduce the aromaticity, that in this way the contribution of the kinetic structure would increase. Normally in the aromatic structure you expect a large contribution from this, but by building in this bridge you increase the contribution of that. And the reason is actually because in this way you build in a 6-membered ring over here, and that's aromatic. So in this way the contribution is decreased, and this would mean a more balanced contribution of these 2 resonance structures, so it would lead to a reduction of the band gap. That was the basic idea. Now later on it showed that actually the structure of this polymer is not aromatic but kinetic. But let's play with aromaticity and see how it affects band gap. So we have a band gap of 1.8. If I go to the kinetic structure, which is non-aromatic, I have a band gap that's much lower. That we have mentioned already. We disturb the aromaticity of the thiophene ring by building in this bridge, and you see that the band gap goes down. If we move from here to the kinetic geometry, what we do then is replace this disturbed aromaticity of the thiophene ring by aromaticity of the benzene ring, which is quite large. And what you see is that the band gap increases again. And actually that was quite some surprise that this predicted band gap fitted very well with observed band gap. But it took a while. Certainly if you look at publications nowadays, still if they publish about isothiophene, they draw this structure, although it's actually this structure. But okay. We can also look at from the viewpoint of the kinetic structure of thiophene. If we move to the isothiophene, well, again, we build in this aromatic structure, so you go from non-aromatic to aromatic and the band gap increases. So all these changes can be relatively easily interpreted by counting the aromatic structures. This is another example. This is polymers that were synthesized by Ferraris some years ago. So this is a derivative of polythiophene, you could say. You annulate another ring, and you see that the band gap goes down quite dramatically. It halves, more or less. What's going on here? It's a question of aromaticity. Besides aromatic systems, you have also anti-aromatic systems, in which a ring structure leads to destabilization. And this part here is anti-aromatic. So you combine 2 aromatic structures with an anti-aromatic one. Also here you have that. And so globally the aromaticity is brought down, so your band gap will decrease. There's also a funny example. So here you have values from theoretical calculations for the different band gaps of the kinetic structure of isothiophene, the aromatic one, and the aromatic thiophene. If you take a copolymer and you would make an average, you will end up with quite close the band gap that you observe. That's also true if you look at this weighted average of the different band gaps of the constituting building blocks leads you to an estimate of the band gap that's close to the experimental one. So it means that this property is additive. So, okay, part of it has to do with the fact that the connection between the repeating units in such a structure or such a structure or such a structure don't differ that much. And it becomes then additive. And this works quite well. So you can almost predict the band gap just by knowing the band gaps of the homopolymers. Now there are other effects. So fundamentally aromaticity, to tune the band gap. There's another effect, of course, torsion angle, a deviation from planarity. Okay, this interaction is perfect when the system is totally flat. If you build in a torsion angle, you will decrease the interaction of these two p orbitals. And that follows a cosinus theta relationship. So with the 90-degree perpendicular, no interaction, no delocalization. And this has been invoked to explain the differences between the band gaps of these type of structures, or in this case, the oxidation potential, and these kind of structures. What I've done here is blocked the pi system by an extra ring. Now, it has to be mentioned that this reduction of the band gap is not only the result of flattening the structure. Because if you look at it from a quantum mechanical, quantum chemical viewpoint, let's say this ring also contributes to the pi system. So there's a kind of substituent effect. So only a part of the change here that you observe can be related to flattening the structure. A better example in that context is polythiophene with the side chain. If you polymerize that with iron trichloride, that's not a very nice method. Typically, you find 25% of defects. These defects are head-to-head defects. And so these chains will interact and they will push the thiophene rings out of each other, so you create a torsion angle. Okay, in 25% of the cases. But that's visible in the band gap because this type of material synthesized by iron trichloride has a band gap of 2 eV. If you have 100% what this structure, regional regularity, the chain always on the same side, you end up with the band gap of 1.8. So this is a better estimate how large this effect of torsion angle can be. It's something in the order of 0.2 eV. Okay, substituent effect. So we have a basic pi system of the repeating unit. This can be tuned by putting on substituents. This can be electron donor substituents or electron attracting substituents. And the question is, what happens with the energy levels? Also, this is very well known and is observed in a very general way. So if you have an electron acceptor group, what you will see is that both energy levels go down, but the LUMO more than the HOMO. So besides that, you will have also a reduction of the band gap. If you put in donors, the reverse happens. HOMO and LUMO goes up, but the HOMO more than the LUMO. And again, you have reduction of the band gap. So normally, except for fluoro maybe, but normally every kind of substitution leads to reduction of the band gap. A special case is when you alternate acceptor substituted systems with donor substituted systems. So in this way you very effectively reduce the band gap. This was demonstrated by Esko Havinga already many years ago when he synthesized this structure. And you can see here donor groups and acceptor groups next to each other. Well, in such cases, you get a very strong reduction of the band gap. But it must be perfectly alternating. That's a condition. What's happening there? Well, actually, one can explain that with the concepts that we have defined before. So if you have an electron-rich system next to an electron-poor system, a contribution as a resonance structure of a structure in which the rich system gives electron density to the poor system will increase. This contribution will increase. It means that you get structures in which you have a double bond here where you had a single bond over there. The higher contribution of this structure leads to reduction of the bond length alternation because you create extra double bond character here. And as the bond length alternation goes down, you lower the band gap. Another way of looking at it is that if you alternate a rich system with a poor system, the resulting system you will get will keep the HOMO of the rich system and the LUMO of the poor system. And so in this way the band gap is strongly reduced. We can demonstrate that. So if I bring together a poor system with a rich system, so these are the relative positions of the energies, levels of the HOMO and the LUMO. Well, as I bring them close together, they will interact, molecular orbital theory, so you get a binding combination and an anti-binding combination. And actually what you see is that the new donor, the new HOMO beta, is somewhat higher than the HOMO of the donor. And the new LUMO is somewhat higher as the LUMO of, somewhat lower beta than the LUMO of the acceptor. So where you had initially these band gaps, you will end up with a much lower band gap. And this works very strongly. So this is a very effective way to lower the band gap. And if you look at the structures that are used nowadays, you see this pattern. Another aspect that is a consequence of this analysis is that if you look at the HOMO, how this HOMO orbital looks like, as it is closer to the HOMO of the donor structure, it will look like, so the contribution in this combination will be largest of this structure, not of this one that will be here. So the new HOMO looks effectively like the HOMO of the donor polymer. And the same is true for the LUMO. This LUMO looks like the LUMO of the electron poor homopolymer. And that has also important consequences for the performance of these type of structures in solar cells. So again, as I mentioned, if you look at the structures that are used nowadays, you recognize this pattern. Poor, rich, that's the poor part, that's the rich part, and so on and so forth. There are thousands at this moment of this type. And indeed, that you get a reduction of the band gap alternation, you can nicely demonstrate, for example, in this structure. This is an electron donor part. Here you have an electron acceptor part. By combining them in one system, you promote electron transfer from this position to that one. And this leads to this resonance form. So the combination here increases the contribution of this resonance form. And you see where you had a single bond over here, you have a double bond over there. So you get a reduction of the bond length alternation. You get a reduction of the band gap. Specifically for these cases, it also implies let's say, a move of the electron density. By incorporating this resonance structure, you move electrons from this position to that one. So there's also displacement in space. Now the nice thing to mention here is that excited state looks like that. So this one describes very well the ground state, but this one describes very well the excited state. So in the excited state, you have transferred an electron from the nitrogen to the oxygen. So there's a displacement in space. And that also contributes to the effective efficiency of these type of materials. But that's another story. Let's look at the orbitals using a simple modeling program. So here you see the acceptor part. This is the donor part. If I look at the HOMO, you see that it's more localized, the orbital, at the rich part. And in the LUMO, it's more at the electron poor part. So you have effectively this effect, and it can be theoretically modeled. Finally, intermolecular effects on the band gap. Well, what if you have not only one-dimensional delocalization, but that these chains interact? Also, this has an effect. That's called deviation from one-dimensionality. Now, there are systems where this is present in the structure, in which you have more a two-dimensional structure. For example, this polyacenes, this is a perilene structure. It's predicted that the band gap in these structures would be 0. Actually, at this moment, graphene is also an example of that. Graphene has a band gap that's 0 because of this deviation of the one-dimensionality. In the polymers themselves, you can also see that effect because of packing, mostly with a crystalline structure. You bring the chains closer to each other, so there's a component of two-dimensionality, and so you see a shift. This is the spectrum in solution, so chains don't interact. This is in the solid state, and you see a shift to higher wavelengths. So actually, we could say a reduction of the band gap. Okay, that's dangerous to say, but actually this shift is a result of deviation of two-dimensionality. So in that way, it occurs in the type of conjugated polymers that we are discussing. Okay, and that's the end of the first lecture.